Dear students, welcome to the course of VLSI Circuits and Systems. Today's topic under basic circuit concepts, we are going to learn capacitance of layers. In the previous topic, we have completed under basic circuit concepts sheet resistance, where we have evaluated the various resistances of the layers starting from metal layer to polysilicon to diffusion layers in a MOSFET. Now let us focus on capacitance of layers, one more important parameter as far as MOS layers are considered. After completion of this lecture, you will be able to examine the concept of area capacitance of layers, which helps in evaluating the effects of interconnections or wiring in the circuits. Going into the details, first of all, the wiring up of circuits takes place through various conductive layers which are produced by MOS processing. So in a MOS circuit, wiring up is not like a discrete element wiring, but that is because of conductive layers. So therefore, one should be aware of the resistive and capacitive characteristics of each layer that is being used for MOS circuit. So concepts such as sheet resistance and standard unit of capacitance helps greatly in evaluating the effects of wiring and input and output capacitances. Area capacitances of layers. So while we have learned the fabrication process, we have observed the conducting layers generally are separated from the substrate each other by the insulating layers, that is dielectric layers, and thus they form a parallel plate capacitive effects. For any layer, knowing the dielectric thickness, that is silicon dioxide thickness, we can calculate area capacitance as with the basic formula C is equal to A epsilon by D, which is elaborated as epsilon naught into epsilon insulator. A is the area and with the divided by D. And each term in this expression have got a representation where D represents the thickness of the silicon dioxide under consideration, and where A represents the area, surface area of the two conducting layers which are separated by the dielectric, and epsilon ins and epsilon naught represents relative permittivity of silicon dioxide, that is 4, and epsilon naught is 8.85 into 10 power minus 14 farad per centimeter, represented as permittivity of free space. So a normal approach always will make the calculation of this area capacitance in terms of picofarad per micrometer square. So just making a small conversion. So normally C is equal to A epsilon by D will be in terms of farad per centimeter square, where area will be represented in centimeter square and epsilon in farad per centimeter and D in terms of centimeter. But as far as area capacitance of layers are considered, we represent it in terms of picofarad per micrometer square. So where we multiply and divide our original expression with 10 power 12 and 10 power 8 respectively in order to get it in terms of picofarad per micrometer square. So here you can look to the table which is given here for the typical area capacitance values of MOS circuits starting from gate to channel, diffusion, polysilicon to substrate, metal, various metals to substrates, and between the metals and metal to polysilicon for various technologies, that is 5 micrometer, 2 micrometer and 1.2 micrometer, and these all are expressed in terms of picofarad per micrometer square multiplied by 10 power minus 4. For example, if you take one cell in this table, for example, I take the gate to channel capacitance, the representation here is 4. This represents in 5 micrometer technology, gate to channel capacitance is 4 into 10 power minus 4 picofarad per micrometer square. That is what this representation is. and whatever that is shown in the brackets is the relative value. So below this one we have 0.25. So this is the relative value, means diffusion capacitance 1 divided by gate to channel capacitance 4. So its relative value is 0.25. Hope that is clear. So we refer to capacitance calculations. Any problem or any expression for capacitance calculations, we should refer to this table for its relative value and original value of the capacitances based on the technology, and then we need to continue with the calculations based on the area of the layers we are interested in. Standard unit of capacitance denoted as Cg. Always, it is convenient to employ a standard unit of capacitance which gives an appropriate value based on the technology, which is denoted as Cg, and it is for gate to channel capacitance of a MOS transistor with the W is equal to L feature size, that is for square, we call it as W is equal to L, is for a standard or feature size or a square known as standard unit of capacitance. So let us solve a few examples on this one. So for example, if I say the technology is 5 micrometer technology, then we can say its lambda value is 2.5 micrometer. So always L is equal to 2 lambda expression, that is based on the generalized lambda based rules. This expression is known to us. So when I say 5 micrometer technology, that is channel length is 5 micrometer. So that represents lambda is equal to 5 by 2 micrometer, that is 2.5 micrometer. So in that case, the standard square gate area will be 5 micrometer by 5 micrometer or 2 lambda by 2 lambda, that is 25 micrometer square. So in this case, the capacitance value would be, from the table you can say 4 into 10 power minus 4 picofarad per micrometer square. So for the same thing, if I make the standard capacitance value, so you should multiply the gate area with the capacitance value what you have taken from the table. So representing it as 0.01 picofarad. So this is represented as standard unit of capacitance for that MOS layer. So consider the area that is defined in the figure here. So in order to get various capacitances of this uh, layer that has been formed, first we need to calculate the relative area. Relative area is nothing but area of the layer under consideration divided by a standard square. So standard square is known to us, that is 2 lambda by 2 lambda. So what is the area of the given layout? So its length is 20 lambda and its width is 3 lambda. So 20 lambda by 3 lambda divided by 2 lambda by 2 lambda represents 15. So this is the relative area. Now we make different considerations. Consider the area in metal 1. Let us consider this area is confined to metal 1. So if this is metal 1, when we want to calculate the capacitance of metal 1 to that of the substrate, what we will be doing? We will be multiplying the relative area what we have calculated with the relative C value, the capacitance value of metal to substrate from the table. So relative area just now we have calculated is 15, and relative C value, capacitance value from the table is 0.075 times the standard unit of capacitance. So in total that is 1.125 times standard square capacitance, we call it as square gate area feature size. So similarly, if you consider this area to be polysilicon, not a metal, so there also capacitance of polysilicon to the substrate, what will be doing? The relative area is same 15, but the relative capacitance value from the table is 0.1. So that is what the capacitance value changes. Similarly with the diffusion also. Hope this is clear. So we shall take one more multi-layer example here, where you can see different hashings for different materials. So this is for metal, and this is for polysilicon, and this is for diffusion. So here we need to calculate the area capacitance values. So now let us consider only the metal area. So here only the metal area means this metal is getting overlapped with polysilicon here. So neglecting that polysilicon, only remaining portion of the metal, the area can be calculated as the length is 100 lambda, width is 3 lambda. So that is 100 into 3 lambda divided by standard gate area is 2 lambda by 2 lambda, that is 4 lambda square. So relative area is 75. So what would be the metal capacitance here? This relative area multiplied by its relative capacitance value from the table. So that is 5.625 times standard unit of capacitance. Similarly, if we consider only the polysilicon area, so here from the figure you can see only the polysilicon area means you should exclude the gate region, that is the transistor region. So this is the polysilicon area and this one is the polysilicon area. So in this case, this area width and length are 4 lambda and 4 lambda. So that is 4 lambda by 4 lambda. And whereas here I have 2 lambda length and 1 lambda length and its width is 2 lambda. So that is 3 lambda by 2 lambda. Put together the total area of polysilicon is 22 lambda square, where its relative area will be divided by the gate area 22 by 4 and multiplied by the capacitance value from the table 0.1, it makes 0.55 Cg. Similarly, only the gate region here we already know, that is directly unit standard capacitance. So here the total capacitance you can put together the sum of the metal capacitance, polysilicon capacitance and the gate capacitance resulting in 7.20 times standard unit of capacitance. Hope this is clear. So based on the topic what we have discussed now, a few lecture level problems have been framed which we will be discussing in our classroom discussion of this topic. That's all for this lecture. Thank you. Happy learning.